And we'll study right now the camshafts. A camshaft has a cam for each exhaust and intake valve. Each cam has a loop that controls the opening of the valves. The height of the loop is proportional to the amount of the valve will open. The camshaft in older engines had an eccentric to operate the fuel pump and a gear to drive the distributor and oil pump. Some diesel engines have cam loops for fuel injectors, fuel injection pumps, and air starting valves. The camshaft fits in a bore above the crankshaft. The bore is either in the center of the block or slightly off to one side, unless the engine has overhead camshafts. Many camshafts are cast iron or steel. Others are forged steel units to reduce weight and added strength. The camshaft in many late model engines is a steel tube with a loop welded to it. In OHV engines or overhead cams, the camshaft loops work with lifters, push rods, and rocker arms to open the valves. As the cam loop rotates, it pushes up on the lifter, which moves the push rod and one end of the rocker arm up. Since a rocker arm is a lever, as that end goes up, the other moves down. This action pushes down on the valve to open it. As the cam continues to rotate, the valve spring closes the valve while maintaining contact between the valve and the rocker arm, thereby keeping the pushed and the lifter in contact with the rotating cam. OHC engines may have separate camshafts for the intake and exhaust valves. As these camshafts rotate, the loop directly open the valves or open them indirectly with cam followers. Rocker arms or bucket-type tappets, the closing of the valves is still the responsibility of the valve springs. Service to the camshaft in OHC engine is usually a part of the procedure for reconditioning the engine's cylinder head. A camshaft is driven by a crankshaft at half its speed. So this accomplished through the use of the camshaft drive gear or drive sprocket that is twice as large as the crankshaft sprockets. So during one full rotation of the camshaft, the intake and exhaust valves open and close once. To synchronize the opening and closing of the valves with the piston and movement of the pistons, the camshaft is timed to the crankshaft. And the actual design of the cams and loops varies with the type of lifter and follower used in the engine. There are 4 distinct types of lifters: solid non-roller, hydraulic non-roller, solid roller, and a hydraulic roller. Camshafts design of a solid and hydraulic non-roller cams are often called flat tappet cams, and the camshaft must be matched with the type of lifter for which it was designed. And we have the camshaft terminology. Many different terms are used to define the specifications of the camshaft. The actual shape of the cam loop is called the cam profile. The profile determines the duration and lift provided by the camshaft. Valves overlap is controlled by the placement of the loops on the camshaft. Camshaft duration is how long the cam holds the valves open. It's expressed in crankshaft degrees. The width of the loop determines the cam's duration, and lift is the distance the loop moves and the lifter or followers to open the valve. And maximum lift is determined by the height of the loop, and the valve is fully open only when the lifter is at the top of the loop. Camshaft lift doesn't always express how far the valve is open. Rocker arms increase the actual amount of valve opening. Both valves are open slightly at the end of the exhaust stroke and the beginning of the intake stroke. This is called the valve overlap, and overlap is critical to exhaust gas scavenging. A camshaft with a long overlap helps empty the cylinders at high engine speeds for improved efficiency. However, since both valves are open for a longer period, low RPM cylinder pressure tends to drop because the amount of overlap has an effect on cylinder pressure. It affects overall engine efficiency and exhaust emissions, and valve overlap also helps to get the intake mixture moving into the cylinder. As the exhaust gases move out of the cylinder, a low pressure is present in the cylinder. This low pressure causes atmospheric pressure to push the intake charge into the cylinder. Less overlap provides for more pressure in the cylinder at low speeds, resulting in more torque at lower speeds. Also, we have the loop terminology, and here some terms are used to describe the camshaft's profile. We have the base circle. The base circle is the cam without its loop. Also, we have the nose. The nose is the highest portion of the cam loop measured from the base circle, and this point provides for the maximum amount of lift. We have the ramp, flank, and the ramps are the side of a cam loop that lie between the nose and the base circle. We have the clearance ramps. Clearance ramps are at the very beginning or end of the opening and the closing ramps. Also, we have loop separation. Loop separation is the angle formed by the center line of the intake and exhaust loops. And we'll move right now to the timing mechanisms. The camshaft and the crankshaft must always remain in the same relative position to each other. They must also be angled to each other, so the alignment is initially set by matching marks on the gears for both shafts. These are called timing marks, and the following are the basic configuration for driving the camshaft. We have the belt drive, which is sprockets on the crankshaft, and the camshaft are linked by a continuous neoprene belt. The belt has square-shaped internal teeth that mesh with teeth on the sprockets, and the timing belt is reinforced with a nylon or fiberglass to give it strength and prevent stretching. This drive configuration is limited to OHC engines. Most technicians replace the belt anytime it has been removed. Also, we have a chain drive. Sprockets on the camshaft and the crankshaft are linked by a continuous chain. The sprocket on the crankshaft is steel. The sprocket on the camshaft is steel on heavy-duty applications. When a quiet operation is gold, an aluminum sprocket with a nylon teeth is used, and nearly all OHV engines use a chain drive system. Chain drives are also used on many OHC engines, especially DOHCs. We have as well the gear drive. A gear on a crankshaft meshes directly with a gear on a camshaft, and the crankshaft gear is usually iron or steel. Also, we have the tensioners. There is a tensioners on a long chain and belt drive, and the tensioners may be spring-loaded and or hydraulically operated. Its purpose is to keep the belt or chain under the correct tension as it wears and stretches. All belts and chains have a drive or tension side and a slack side. The tension side is the side that is always being pulled, and the tensor side is positioned on the slack side and presses on the belt or chain. Also, there is a variable valve timing, or VVT. The variable valve timing or VVT system electronically adjusts valve overlap by changing exhaust valve opening times in response to engine speed and load. The system provides an increase in horsepower and torque. It also reduces fuel consumption and exhaust emission. Also, we have the valve lifters. Valve lifters, sometimes called cam followers or tappets, follow the counter or shape of the cam loop. Lifters are either mechanical, solid, or hydraulic. Solid valve lifter provides a rigid connection between the camshaft and the valves. Hydraulic valve lifters provide the same connection but use oil to absorb the shock that results from the movement of the valve train. And hydraulic lifters are designed to automatically compensate for the effects of engine temperature. Changes in temperature cause valve train components to expand and contract. Hydraulic lifters automatically maintain a direct connection between valve train parts. Solid lifters do not have this built-in feature and requires a clearance between the parts of the valve train, and this clearance allows for components expansion as the engine gets hot. Periodic adjustment of this clearance must be made, and excessive clearance might cause a clicking noise, and this clicking noise is also an indication of hammering of valve train parts against one another, which results in reduced camshaft and lifter life. So, non-roller lifters rotate in their bore. The contact area between the cam loop and lifter is one of the highest stressed area in an engine. So lifter rotation places this stress at different areas at the bottom of the lifter and prevent excessive wear. So cam loops are ground with a slight taper, approximately 0.254 millimeter, and the diameter of the front of the loop's base circle is different from the diameter at the rear of the loop. So the speed at which the lifter rotates in its bore depends on the amount of taper. So the interface of the lifter and loop taper also prevents the camshaft from moving to the front or rear while the engine is running. We have as well the roller lifters. In an effort to reduce the friction of the lifter rubbing against the cam loops and the resulting power loss, manufacturers often use roller-type lifters, which is roller lifters, and have a roller on the camshaft end on the lifter. Also, the roller acts as a wheel and allows the lifter to follow the counter of the cam loop with a little friction. The lifter rolls along the surface of the loop rather than rub against it, so roller lifters may be solid or hydraulic. The hydraulic part of roller lifter works in the same way as the flight hydraulic tappet. The rollers also allow the lifter to follow aggressive cam loop designs that provide more lift at a given duration than a flat tappet. We'll move right now to the operation of hydraulic valve lifters. A hydraulic lifter has a plunger, oil metering valve, pushrod seat, check valve spring, and a plunger return spring housed in a hardened iron body. When the lifter is resting on a cam's basic circle, the valve is closed and the lifter maintains zero clearance in the valve train. Oil is fed to the lifter through fed holes in its bore. Oil pressure forces the lifter check valve closed to keep the oil inside the lifter, and this forms a rigid connection between the lifter and pushrod. When there is some clearance in the valve train, a spring between the plunger and lifter body pushes the plunger up to eliminate the clearance. As the cam loop turns and opens the valve, the lifter's oil feed hole moves away from the oil feed in the lifter bore. So new oil can't enter the lifter. The effort to open the valve pushes the lifter's plunger down slightly, and this allows a small amount of oil to leak out. This is called leak down. So when the lifter returns to the base of the cam, oil can again fill the lifter. So we have as well the camshaft bearings. The camshaft is supported by several bearings or bushings. OHV camshaft bearings are one-piece plain bearings pressed into the camshaft. Before the bearings are either aluminum or steel with a lining of babbitt. Babbitt is a soft, slippery material made of mostly lead and tin. Alloys of aluminum are commonly found in late model engines. Aluminum bearings have a longer service life because they are harder than babbitt, but they are more susceptible to damage from dirt and poor lubrication. So OHC camshaft may be supported by split plain bearings. These split bearings are similar to the main and connecting rod bearings. Camshaft bearings are normally replaced during engine rebuilding, and the old bearing should be inspected for signs of unusual wear that may indicate an oiling or bore alignment problem. Also, we have a balance shaft, has a counterweight designed to mirror the throws of the crankshaft. These weights are positioned to the opposite side of the weight of the crankshaft and are rotated in the opposite direction as the crankshaft. Balance shafts are located in the engine block on one side of the crankshaft, in the camshaft bore, or in separate assembly bolted to the engine block.